Now that we know how to determine if an equation is separable or not, how do we use that to find a solution analytically? So what we want to do is we want to put all the pieces with y and dy on one side and all the pieces with x and dx on the other side. So this first question I want to look at, number 7, dy dx is equal to x plus 1 quantity squared. Okay, so I have a function of x here, and my function of y is just trivial. It's just a 1, which will make this a little bit easier for our first problem. What I'm going to do is I'm going to multiply this dx over. So I get dy is equal to x plus 1 quantity squared dx. Okay. And if I had something with a y over here, I would divide it over to this side. So I'd have all the y dy pieces together and all the x dx pieces together on separate sides. Okay, so hence the name separable equations. Once you've done that, you're going to do the integral of both sides. Okay, so we're going to find the antiderivative here. This looks like I'm going to need a little u sub. So u is going to be x plus 1, and my du is dx, which is nice. So the integral of dy is y. And the integral of this, so this would be u squared, which would give me a u cubed over 3 plus Charlie. And so that u is my x plus 1. So I get y is equal to x plus 1 quantity cubed over 3 plus Charlie. Now, there are two indefinite integrals here, and you could have a plus c1 here, and you could call this one a plus c2. And this happens a lot in differential equations. We end up with all these multiple different plus C1, C2, C3s floating around. And what we do is we just round them all up at the end and we combine them into one. So if you had done that, what you would do is kind of your last step here would just be to write this as a plus C. Sometimes you'll see people swap out all the C's for an A or a B or some capital A or capital B, something like that. That's pretty common too. Okay? But we just round all those constants up together and turn them into one. All right, let's look at number 8. So this one has an x and a y in it, so it'll be a little more interesting. We'll start by getting dy dx on one side by itself, and I'll do that by subtracting the 2xy squared over to the other side. I'm going to multiply my dx over here. Oops, that should be a negative 2xy squared since we subtracted. So I'll multiply this dx over. So you get a negative 2x dx, and I'm going to divide this y squared to the other side. So I get a 1 over y squared dy equals my negative 2x dx. So the integral of y to the negative 2 dy equals negative 2 times the integral of x dx. Okay, so all I did was just rewrite that into a form, a calculus-ready form, so I'm ready to find the antiderivative. So get y to the negative 1 over negative 1 equals negative 2x squared over 2 plus Charlie. And that gives me negative 1 over y equals negative x squared plus Charlie. And I could leave it there. This one's not too bad to solve for y, so I'll go ahead and do that. It gives me y is negative 1 over negative x squared plus Charlie. So there is a solution there for number 8. And then let's take a look at number 9. So number 9 requires a little bit of algebra here. So we can rewrite this as e to the 3x times e to the 2y. So now I have two separate pieces, one piece in x and one piece in y, which makes it separable. So I'll multiply this dx over, and e to the 3x dx, and I will divide this e to the 2y back to the other side. So 1 over e to the 2y dy equals e to the 3x dx. So this is the integral of e to the negative 2y dy equals the integral of e to the 3x dx. And this is going to require a u sub for both of these pieces. So u is negative 2y, du is negative 2 dy. So negative 1/2 du equals dy. And for the right side, I have u is 3x. So du is 3 dx. And 1/3 of du is dx. All right, so my antiderivative here is negative 1/2 e to the negative 2y is equal to 1/3 e to the 3x plus Charlie. Okay. And then as far as simplifying this, it's going to be kind of ugly. We could certainly multiply this negative 2 over here. And then I could apply the natural log to both sides, so I could try and get at this y, but it's going to get really muddled. So in this case, it's not really worthwhile to solve for y, so I'll just leave my solution there. All right, so hopefully that gives you an idea of how to solve separable differential equations and why they are so nice.